Our universe is a vast and mysterious place, filled with billions of galaxies, each teeming with billions of stars. But how did it all begin? How did this magnificent cosmos arise from nothing? The answer, according to the prevailing scientific theory, is the Big Bang. About 13.8 billion years ago, our universe was born from a single point of unimaginable density and temperature called a singularity. In a fraction of a second, this singularity expanded at an incredible rate, an event we call the Big Bang. From this fiery, chaotic beginning, the universe as we know it emerged. The Big Bang theory is not just a guess, it is supported by a wealth of observational evidence. From the cosmic microwave background radiation, the faint afterglow of the Big Bang, to the abundance of light elements in the universe, all signs point to this grand event. The story of the Big Bang is a story of incredible transformation. From the formation of the first particles to the birth of stars and galaxies, it is a journey that continues to this day as the universe expands and evolves. So, let us embark on this cosmic adventure to understand our place in this grand scheme of things. Imagine a point smaller than the smallest atom, yet containing all the matter and energy that would become our universe. This is the Singularity, a point of infinite density and temperature where the laws of physics as we know them break down. At this moment, time and space as we understand them did not exist. The Singularity represents the very edge of our current understanding of the cosmos. It is a realm where our current theories are insufficient to fully describe what was happening. The conditions present in the Singularity are impossible to recreate in any laboratory on Earth. The temperatures and pressures were so extreme that even the very fabric of space-time was warped beyond recognition. It is a realm of pure speculation, where the known laws of physics collapse. Despite the mysteries surrounding it, the Singularity is a crucial part of the Big Bang theory. It is the seed from which the universe sprouted, the ultimate origin point of everything we see around us. In a sudden burst of expansion, the universe erupted from the Singularity. This wasn't an explosion in the conventional sense, like a bomb going off in a pre-existing space. Instead, it was the expansion of space itself, an inflationary period where the universe grew exponentially in size. As the universe expanded, it also cooled. This cooling was crucial for the formation of the structures we see today. Imagine a blacksmith plunging a hot iron rod into cold water. The sudden cooling causes the metal to harden and take shape. Similarly, the cooling universe allowed energy to convert into matter and forces to separate. This expansion wasn't a smooth, uniform process. Tiny quantum fluctuations in the early universe provided the seeds for the large-scale structures we see today. These fluctuations created regions of slightly higher density, which would later, under the influence of gravity, grow into galaxies and galaxy clusters. The expansion of the universe continues to this day, a testament to the Big Bang's enduring legacy. As we observe distant galaxies speeding away from us, we are witnessing the after effects of that primordial expansion. In the first fractions of a second after the Big Bang, the universe was a seething cauldron of energy. Within this chaotic environment, the fundamental forces of nature began to emerge. Gravity, the force that binds planets, stars, and galaxies together, was the first to separate. Next came the strong and weak nuclear forces, responsible for holding atomic nuclei together and governing radioactive decay. Finally, electromagnetism, the force that governs light, electricity, and magnetism, emerged. These forces, once unified at the extreme energies of the early universe, now govern the interactions of all matter and energy. The separation of the fundamental forces was a pivotal event in the evolution of the universe. It set the stage for the formation of particles, atoms, and eventually all the complex structures we see today. Imagine a sculptor with a lump of clay. The clay represents the primordial energy of the universe, and the sculptor's tools are the fundamental forces. Just as the sculptor uses different tools to shape the clay, the fundamental forces shaped the early universe, giving rise to the building blocks of matter. As the universe continued to cool, energy began to condense into matter, following Einstein's famous equation E=mc². This period is known as the particle era, a time when the universe was a hot, dense soup of elementary particles. Quarks, the fundamental building blocks of protons and neutrons, zipped around at incredible speeds, colliding and interacting with each other. Electrons, much lighter particles with a negative charge, also filled the universe. Alongside these familiar particles were more exotic forms of matter and antimatter, constantly created and annihilated in the intense energy of the early universe. This period was marked by a delicate balance. For every particle of matter created, an antiparticle with the opposite charge was also formed. When matter and antimatter meet, they annihilate each other, releasing a burst of energy. Fortunately for us, a slight asymmetry existed with a tiny excess of matter over antimatter. This slight imbalance allowed matter to survive and eventually form the universe we observe today. This matter-antimatter asymmetry remains one of the biggest unsolved mysteries in cosmology. From plasma to atoms, the first light, about 380,000 years after the Big Bang, the universe had cooled enough for a momentous event to occur, the formation of atoms. Before this time, the universe was filled with a plasma, a state of matter where electrons are stripped from their atomic nuclei. As the universe cooled, the electromagnetic force was finally able to bind electrons to atomic nuclei, creating the first atoms of hydrogen, helium, and lithium. This period, known as recombination, marked a profound change in the universe's properties. Before recombination, the universe was opaque, like a dense fog. Light or photons were constantly scattered by free electrons, unable to travel far. However, once atoms formed, the fog lifted. Photons were now free to travel unimpeded, and the universe became transparent. This first light, released during the era of recombination, is still detectable today as the cosmic microwave background radiation. It provides us with a snapshot of the universe as it was just 380,000 years after the Big Bang, a baby picture of the cosmos.
The formation of the first atoms set the stage for the birth of stars and galaxies. Gravity, the force that governs the motion of celestial bodies, began to pull together the primordial gas clouds.
These gas clouds, primarily composed of hydrogen and helium, began to collapse under their own gravity, forming dense regions known as protostars. Within these protostars, nuclear fusion ignited, giving birth to the first stars.
These early stars, known as population 3 stars, were massive, hot, and short-lived. They forged the first heavier elements like carbon and oxygen in their cores.
As these stars died in spectacular supernova explosions, they seeded the universe with these new elements, enriching the cosmic environment. This process of star formation and death continued, leading to the creation of galaxies, the vast structures that populate the universe today.
The universe, ever expanding, continues its journey through time and space. The formation of elements and the birth of stars and galaxies are ongoing processes.
Every star we see in the night sky, every galaxy we observe with our telescopes, is part of this grand, never-ending cosmic story.
Our own solar system, formed about 4.5 billion years ago, is a product of this cosmic evolution, born from the remnants of previous generations of stars.
As we look deeper into the universe, we are also looking back in time, witnessing the history of the cosmos unfold before us.
Amidst this vast and intricate cosmic tapestry, we find our place. Our planet Earth is but a tiny speck in the grand scheme of the universe.
Yet, from this small vantage point, we've been able to explore and understand the cosmos, uncovering its secrets and marveling at its wonders.
The journey of discovery is far from over. With each new observation, each new discovery, we add another thread to the ever-growing tapestry of our understanding.
And so, as we continue to explore, we remain in awe of the universe's beauty, complexity, and the profound connection we share with it.